Hi, welcome to my channel. Today we are going to discuss a very important and fundamental question in deep learning. We want to understand whether a network of neurons can be used to represent an arbitrary function like the one shown in this figure. The question here is clearly nonlinear, irregular, and complex. The key question is, can a neural network approximate such a function using simple neurons? This question leads us to the core idea behind the universal approximation capability of the neural networks. Let us make a simple but powerful observation. If we approximate the function using a collection of vertical bar-like functions, then their combination can closely follow the original curve. Each bar captures a small portion of the function. Now notice something important. If we use few bars, the approximation is rough. If you use more bars, the approximation becomes better. So the accuracy depends on how many such basic components we use. What we are essentially doing here is adding multiple vertical bar functions together. Each bar contributes a small local effect, and the summation of these bars gives us an approximation of the arbitrary function. This idea is extremely important. A complex function can be represented as a sum of simpler functions. Now, the natural question is, how does this idea connect to the neural networks? Now, let us connect this idea to a network of neurons. Each vertical bar can be thought of as the output of a hidden neuron. All the hidden neurons receive the same input X, but each neuron responds to differently because of different weights and biases. These hidden neurons outputs are then summed at the output neuron. So hidden layer creates individual bars, output layer adds them together. This is exactly how a multi-layer perceptron works. Now we reach a crucial question. We have seen that summation of bars can approximate any function, but the big question is, how are these vertical bars actually formed by neurons? To answer this, we need to look closely at how activation functions, especially sigmoid, behave. Let us examine the sigmoid function with different weights and biases. As the weight increases, the sigmoid becomes steeper. As we change the bias, the sigmoid shifts left or right. In the limit of large weights, the sigmoid behaves like a sharp step function. So a sigmoid neuron can act like a smooth vertical edge. Now comes the key construction. If we take one sigmoid that rises at point A, another sigmoid that falls at point B, and the subtract them, we get bar x equal to h times between subtraction of two sigmoid function with parameter x minus a and x minus b and k. This gives us a single vertical bar. Here a and b define the left and the right boundaries. H controls the height of the bar. K control how sharp the edges are. This is how one hidden neurons pair can create one bar. Finally, let us interpret this in terms of neural network. Each bar is created by two neurons, one neuron with positive weight, one neuron with negative weight. These outputs are combined in the next layer. By using many such neuron pair, we can create many bars. And by adding all these bars, the network approximates an arbitrary function. This is the intuition behind why neural networks are universal function approximators. To summarize, a neural network approximates any arbitrary function by creating local feature using hidden neurons, combining them through weighted summation, and refining the approximation as the number of neurons increases.